Hey guys, this is 5.3 notes on medians and altitudes. So we'll start off with some definitions. So the first one is a median. So a median of a triangle is a segment whose endpoints are a vertex of the triangle and the midpoint of the opposite side. Every triangle has three medians, which are concurrent. Okay. The point of concurrency of these medians of the triangles is the centroid. Okay. This centroid is always inside your triangle. Now, let's talk about the centroid theorem. Okay, so the centroid of a triangle is located two-thirds, so that's important, it's two-thirds of the distance from each vertex to the midpoint of the opposite side. Okay, so let's look at some of the lines, and then so let's look at this AP line, right? Oh, let me make this blue. All right, so we see AP there, okay, and then we also see the full AY, right, that goes through that point P, okay, and their centroid theorem tells us that this AP, okay, is going to be two-thirds that whole AY. Okay, so the whole piece, right, is AY, and then AP is going to be two-thirds of it. Okay, so that's the centroid. It's two-thirds of the way through. Okay, so let's look at a couple other ones, right? If we look at, say, BZ. Oh, sorry, BP. All right, we know BP is going to be two-thirds that full BZ. And then the last one, we have CP. So that means CP is going to be two-thirds of the whole distance of CX. So now let's do some examples using the centroid theorem. We'll look at this triangle over here and some of the information given, and then we're going to find a certain length. Okay, so this one we're looking for LS. So we're trying to find LS right here. Right. If we look at the centroid theorem, we know that LS is going to be two-thirds that whole piece. So L to R. Okay, so now our objective is to get that distance LR somehow, or RL somehow. Well, if we look up here, actually I'll underline it blue, we're given RL is 21. So in order to solve for LS, we're just going to plug in 21 in for RL or LR. And a little bit of multiplication, right? we should get 14 is 2/3 of 21. So LS is 14. Now the next one, we're looking for NQ. Okay, so NQ is the full piece. Okay, so that's important, right? The full piece, NQ, right? We know if we take 2/3 of it, it's going to be equal to that NS piece, or centroid, right? Now, if we look at some of our information, right, and we go back up top, it says SQ is equal to 4. So we're given that length right there is 4. Well, if NS, right, is 2/3 of the full NQ, then SQ has to be that remaining 1/3. So we should know SQ is equal to 1/3 of that NQ, right? That full piece, right? Because we know NS is 2/3, so that means SQ needs to be 1/3, right? So it adds up to 3/3. Now we can use this information to solve for our NQ, right? So we know SQ is equal to 4 from up top. And then what we need to do is divide by 1/3 or multiply by the reciprocal. So when we do that, we get 12 is equal to NQ, right? Because 1/3 of 12 is 4, right? Therefore, NQ has to be 12. Now, if we move on, we're going to go to the next definition. So we talked about medians and centroids. Now we're going to talk about altitudes. So altitude of a triangle is a perpendicular segment from a vertex to the line containing the opposite side. And every triangle will have 3 altitudes. And they can either be inside, outside, or on the triangle. Okay. So to show you, right, the different types of altitudes for different triangles, we'll look at an acute triangle, a right triangle, and then 3 altitudes for obtuse triangles. Okay, because we're going to be able to get 3 for different 3 types of altitudes for obtuse. So an altitude for acute, right, we said it's the perpendicular bisector from a vertex to the line containing the opposite side. Okay, so right, if we start here at a vertex and then we have a perpendicular bisector right here, that is going to be our altitude, right? We'd also do it from here. So it makes another perpendicular bisector, right? That could be our altitude. And then also from this vertex, making a 90-degree angle or perpendicular bisector. So either one of those can act as our altitude. All right. So now for right triangles, we're only going to have one. Right. It starts at our vertex and it goes right to make a perpendicular bisector, and that's our altitude for a right triangle. All right, now, right, we know we have 3 vertices for obtuse triangles. So, right, if one is starting at B, right, then we need to make a perpendicular bisector. So that's straight down right here. So it makes perpendicular bisector. Okay, so that's one way. Say we started at A, right? Our altitude would look like this. Sorry, that's starting from C. And then starting from A, right, it looked pretty similar to a right triangle. where it's starting at A and then making a perpendicular bisector on that opposite side. Okay, so this is what the altitudes could look like for acute, right, and obtuse triangles. And then the last kind of definition that goes along with altitudes is the point of concurrency of the altitudes of a triangle is going to be called the orthocenter. So orthocenter. And we're going to have to solve for these orthocenters. Okay, so again, that's the point of concurrency of the altitudes of a triangle, and that's called the orthocenter. So if we look at our image over to the right, you'll see that right here is where all the altitudes are meeting. Okay, so that would be our orthocenter of the triangle. And now we're going to have to find orthocenters given certain vertices on a coordinate grid. Okay, so and then we're going to go through like each step on how to solve this. Okay, so the first thing you could do is actually make the triangle. So our x is at 3, -2. So here's our x. Our y is at 3, 6. Here's our y. And then our z is at 7, 1. So 4, 5, 6, 7, 1. Here's our z. Okay. This is the triangle we're using, right? And what we're going to do is find an equation of the line containing the altitude from z to xy first, right? So start at z, right? That's one of our vertices. And then to make a perpendicular bisector, or that altitude, right, we would be going straight into right here. And this would be our line, okay, or our altitude, right? So if we look at that, that line is just the line y equals 1, right? It doesn't have a slope, so there's no number times x, right? And then its y-intercept is at 1. So the equation of this line is just y equals 1. Right? Now, our next step is to find the equation of the line containing the altitude from y to xc. So start at y and go through xc, right? So that means we're starting at the point y, and we need to go through this xz line somewhere, okay? But the problem is we actually need to find the equation. We need to solve for this one because we know the one through z was pretty easy. It was just a straight line, so you didn't have to really solve for the equation. But this one, you actually have to use the points, so we need to find the slope, then the perpendicular slope, and then we need to find the equation. Okay, so right, we're going from y to yz, xz. Right, so we're looking first for the slope of xz. Okay. Well, how do we find the slope of this line xz? We're trying to find that slope. Well, you can either use the slope formula or you can look at the picture. So goes up 3 to the right 4, right? The line of this slope. So it's 3/4. Now, right, that's the slope of that line. But we're looking for the perpendicular bisector for the altitude. So we need the perpendicular slope to that. To find the perpendicular slope, right, it's the opposite reciprocal. So it's negative now because it was positive before, and then we flip the numerator and denominator, so our perpendicular slope is 4/3 because we want that line perpendicular to that xz. Okay. The point we're going to use, right, is 3, 6 because that's our y point. That's where y is at on the coordinate plane, right? And now we're going to use the slope formula. Okay, so we're going to use y minus y1 equals m times x minus x1, right? We know this is our x1, here's our y1, and this is our slope, right? So just substitute in, and then we'll get our equation. So y minus 6 equals negative 4/3 times x minus 3. We get y minus 6, negative 4/3 x, and now, right, we do negative 4/3 times negative 3, right, we get positive 4. Okay, so what's left over here is plus 4 when you're distributing that negative 4/3 to negative 3. Now just add the 6 to the other side, we get y equals negative 4/3 plus 10. And that is that equation from here, like that. And then the last part of this problem is solving for the coordinate of the orthocenter. So where those three vertices meet at, those altitudes meet at. So we want to solve this. And to solve it, we're going to set up a system, right? So it says solve the system. Well, our system is just the two equations that we found. Okay, you only need two of them out of the three. Our one equation was y equals 1. And that was from part B. And then we also found another equation in part C, which was y equals negative 4/3 x plus 10. Right? So now we just need to solve this system. Okay. Well, how do we solve it? We know y is equal to this and y is equal to this. If they're both equal to something, we can set these two things equal to each other. So 1 equals negative 4/3 x plus 10. Right? We can set these two equations equal to each other because they both equal y. Now we get negative 11. Oh, sorry, I lied. Negative 9 is equal to negative 4/3 x. And then we just need to multiply by negative 3/4. Right. And we should get 6.75 is equal to x, or if you did a fraction, right, it'd be 27/4 is equal to x, right? And we already know what our y is going to be, right? Because we have y equals 1 and then x equals these. Okay, so our final coordinate, if you want to write it in decimal, it would be 6.75 comma 1. And that is where our orthocenter would be for this problem. And that's the end of the notes. So please ask me any questions on Reminder, Google Classroom, if you have any on this stuff before you get into doing any worksheets or problems on Math Excel.